The allocator in the computer is a program. After we input some numbers, we need to remember it temporarily. Usually stored in memory, it will have these contents. Among them, the place where these numbers can be stored is called a heap. So how big should the heap be? For example, the user may enter 3 numbers, so using 3 cells to store it is just right. However, if the user enters 7 numbers next time, it won't be able to put it down. Either put a large enough space, such as 10 cells, then it will be fine. However, users usually only enter 2 to 3 numbers, and the remaining useless are too wasteful. Therefore, when the program is running, after the user enters the number, a better way is to count a number and get the number 3, and then decide how much cell space to allocate. This type of dynamic allocation at the runtime is called dynamic allocation. Therefore, in memory, the heap sometimes need to grow upward to obtain more storage space during dynamic allocation. For example, in this heap, a unit needs to be dynamically allocated, called a heap block. The pipe block can be large or small, dynamically designated. Then allocate another piece, and then another piece. At this time, the middle heap block is no longer used and released. The free block in the middle is called the free block. The allocated blocks are called allocated blocks. So how do we manage these blocks? The simple way is to string them together. Then start from the beginning, traverse one by one until the specific block is processed. So how do we do it? We add a header to each blocks to indicate the size of the entire block. The actual storage space is called the payload, and the pointer returned to the developer is the starting address of the actual storage. At the same time, the memory in the heap generally uses 8 bytes as the basic unit. Therefore, each block actually needs to be aligned. Then there is a tail as a padding. Therefore, the block size is equivalent to the sum of these 3 parts. Then, after knowing the starting address of the heap, according to the size of the block header, you can offset to the end, which is the starting address of the next block, and continue the offset just now. In this way, traverse is achieved. Then the header here is 32 binary serials, which is 4 bytes. We add binary 8. If you add 2 8s, it is a multiple of 8. We found that the 3 rightmost bits are always 0. It seems useless. Then we make fun use of it and gives the ones a special meaning. If it is 0, it means that this block is a free block, and if it is 1, it is an allocated block. This is also one of the benefits of alignment. Then, the application developer using the malloc function in the C language can allocate a heap block, for example. After obtaining its starting address, you can access this area. Then, when it is not in use the free function to release it, which means it becomes a free block. The specific operation on the memory here is responsible for the dynamic allocator in the C language. But sometimes the immediate release is forgotten, causing errors and waste. Therefore, languages such as Java will be automatically released, which is called garbage collection. Specifically, we add numbers to allocated blocks in the heap, connected to each other. There are one or more root nodes pointing to block 4 outside. Converting to a directed graph can be better understood. The first step is to start from root node and follow the connection to traverse all reachable heap blocks and mark them. In the actual heap, this is the case. In the second step, what remains unmarked is unreachable garbage, which need to be released immediately. Together, they are called the mark and sweep garbage collector. This is just one of our algorithms. Okay, that's all for today's video. See you in the next issue.